This is chloroform, with the chemical formula CHCl3. It is a polar molecule composed of a central carbon atom represented by this green pom-pom, and 3 chlorines, which are these orange ones, and also 1 hydrogen, represented by this little blue guy. The intermolecular forces present in chloroform include dipole-dipole, which is represented by this elastic band, and London dispersion. The dipole-dipole forces are due to the permanent dipoles created by the difference in electronegativity between carbon, hydrogen, and chlorine. Also, chloroform molecules experience London dispersion forces. However, the dipole forces take charge because they're stronger. Chloroform exists at liquid at room temperature. This is because of the combined effect of dipole-dipole and London dispersion forces, which are strong enough to hold the molecules together in a condensed phase, allowing them to flow as a liquid. However, these forces are not strong enough to hold a molecule in a solid form.
Chloroform melting and boiling points are influenced by the intermolecular forces at play, primarily dipole-dipole and London dispersion forces. Dipole-dipole interactions arise due to the permanent dipole moments in chloroform molecules created by the difference in electronegativity between carbon, hydrogen, and chlorine atoms. These forces contribute to the stabilization of the liquid and solid phase, requiring more energy to break the bonds during phase transitions. Additionally, in London dispersion forces resulting from temporary fluctuations in electron distribution further enhance intermolecular attractions in chloroform. The cumulative effects of primarily dipole-dipole interactions and London dispersion forces being relatively weak compared to intramolecular forces contribute to the relatively low melting point of chloroform of 61.2 degrees. This is because not an extremely large amount of thermal energy is needed to break the dipole-dipole bonds, turning it into a gas. These weaker bonds also relate to the higher melting point of chloroform, being at negative 63.5 degrees Celsius, as those molecules with stronger forces present will exhibit lower melting points due to more energy being required to break the bonds. This is methane, represented by the chemical formula CH4. The intermolecular forces present in methane are primarily London dispersion, represented by this coil here. This coil represents London dispersion, as it is not as strong as this elastic band that represents dipole-dipole in CHCl3. See here, electrons are not always static. They actually move around frequently, and that is what creates London dispersion forces, also known as temporary dipoles. Also, despite being nonpolar, methane molecules attract each other through these temporary dipoles. However, these are very weak intermolecular attractions. In its present state, methane exists as a gas. This is because the weak London dispersion forces, seen here, are not strong enough to hold them together in a condensed phase, allowing them to float freely as a gas. Methane has a low boiling point because it has very weak intermolecular forces of attraction. To boil methane, energy must be added to it. The energy being added is allowing the methane molecules to overcome the attractive forces. Because these attraction forces between methane molecules are very weak, little energy is required to convert methane into a gas from a liquid. The weak London dispersion forces between methane molecules result in a weaker structure compared to the stronger intermolecular forces, such as dipole-dipole or hydrogen bonding in other molecules. When heat is applied, it takes less energy to break these weak bonds, allowing methane molecules to transition from a solid to a liquid or a liquid to a gas at a relatively low temperature, hence the lower melting points. Now let's look what happens when chloroform vaporizes. Initially in its liquid phase, chloroform molecules are closely packed together, held by dipole-dipole and London dispersion forces. These intermolecular forces keep the molecules relatively stationary, but allow for some movement, resulting in the liquid's ability to flow. As heat is applied to the liquid, the molecules gain kinetic energy, causing them to vibrate and move more vigorously. With increased kinetic energy in chloroform, some molecules near the surface gain enough to overcome the intermolecular forces holding them in its liquid phase, breaking them. These molecules break free from the liquid surface and enter the gas phase in a process known as vaporization. In its gas phase, chloroform molecules move freely and independently with no fixed arrangement.